A review of criticality accidents, Part 4, Mayak Production Association, 2nd January 1958. Uranyl nitrate solution, U90, in an experiment vessel. 1 prompt critical burst. 3 fatalities, 1 serious exposure. This particular accident was unique in that it occurred during operations with a vessel used for in-plant critical experiments. However, since the accident occurred well after the cessation of an experiment and during handling operations associated with transferring the fissile solution into favorable geometry bottles, it has been categorized as a process criticality accident. After the 21st of April, 1957 accident, it was decided to set up a small-scale experiment capability for measuring the critical parameters of high-concentration, highly enriched uranyl nitrate solution. This was deemed necessary in light of the widespread use of unfavorable geometry process vessels, the uncertainties in the critical parameters, and in recognition of 2 prior criticality accidents at the same plant. Previously, critical vessel dimensions and critical solution concentrations, masses, and volumes were estimated based on calculations, since directly applicable experimental results were unavailable in Russia at that time. The experimental capability was set up in the same building where large volumes of this material were being processed, giving efficient access to the fissile solution. The small critical experiment setup, shown in Figure 8, was located in a separate room in the main process building. It had only been in operation for 2 months at the time of the accident. During measurements, the critical experimenters worked at a control panel located a few meters away from the setup and shielded by a 500 mm thick, water-filled slab tank located 600 mm from the experiment vessel. There were no criticality alarms installed in the building. This was the first day of work after the New Year's holiday. While the plant generally ran continuously on 4 6-hour shifts daily, there was only one team of critical experimenters. They were working on their first shift of the new year, 1300 to 1900. Other plant operators were involved in preparing the fissile solution and in assembling the experimental apparatus, but the critical experiments were performed solely by this dedicated, knowledgeable team. The prior series of experiments had focused on determining critical parameters for smaller vessels and had been concluded before the end of the year. During the last working days of December, the equipment for the next experiment series had been assembled. This was the first experiment conducted with this larger vessel. It was a cylindrical stainless steel vessel, 750 mm inside diameter, with a wall thickness of 2 to 4 mm, representative of the vessels in common use at the facility. The fissile solution of known concentrations and volumes was added from an overhead graduated cylinder, 3 liters in capacity. The experiment vessel was bolted to a stand and sat atop an 8 mm thick steel support plate approximately 0.8 meters above the concrete floor and at least 1.5 meters from any walls. Thus it was without appreciable reflection, approximating many in-plant situations. The vessel capacity was in excess of 400 liters, permitting critical states to be measured over a wide range of conditions. A central guide tube accommodated a neutron source, and the leakage neutron flux was monitored with a BF3 proportional counter located beneath the tank. Approach to critical measurements employed the standard inverse multiplication technique. After each experiment was completed, written procedures called for the solution to be drained through a line to favorable geometry 6-liter bottles. This process was to be repeated until the entire experiment vessel had been drained. After filling some of these 6-liter bottles, the experimenters judged the remaining solution volume to be highly subcritical. It was then decided to circumvent the routine, tedious draining process and manually pour the remaining solution of 418 grams U90 per liter from the vessel. There are no records of the molarity of the solution. To accomplish this, the neutron source and its guide tube were removed and then the vessel was unbolted from its stand. Then 3 of the experimenters manually lifted the vessel and began to move it, in order to directly pour the contents into containers, when the excursion occurred. They immediately noticed a flash, due to Cherenkov radiation, and simultaneously fissile solution was violently ejected, reaching the ceiling about 5 meters above. The 3 experimenters dropped the vessel and, along with a 4th experimenter, who was located about 2.5 meters away from the excursion, went immediately to the change room, showered, and were transported to the hospital. The combination of additional reflection from the 3 experimenters and the change in geometry of the solution volume was sufficient to cause the system to exceed prompt critical. The small neutron background, estimated at only 100 neutrons per second, apparently also contributed to delayed initiation and thus to increased excursion energetics. Based on fission product activity in the solution, the single pulse yield was evaluated to be approximately 2 × 10⁻17 fissions. Total neutron and gamma absorbed doses were estimated at 6,000 plus or minus 2,000 rad for the 3 who lifted the tank and 600 rad for the co-worker at 2.5 meters. The 3 massively exposed workers died in 5 to 6 days. The 4th experimenter survived but had acute radiation sickness, followed by continuing health problems. She developed cataracts and lost sight in both eyes some years later. Due to the severe consequences of this accident, the experimental apparatus was disassembled and the critical experiment program at the plant was terminated. Some of the factors that contributed to the accident are listed below. Violation of the procedures that stipulated the complete draining of the experiment solution into 6-liter bottles. Unbolting and removing the experiment vessel when it contained solution. This was not specifically permitted in the operating procedure. The design of the experiment stand that made it relatively easy to unbolt and remove the experiment vessel. The additional reflection provided by the operators and by lowering it closer to the floor. The lack of knowledge and awareness of the operators as to the large reactivity changes that can occur with shape changes of solutions.